This is lesson 9, cell potential. So why do the electrons move from the anode to the cathode in a voltaic cell? Well, the reason that they move is because of a difference in potential energy. And if you remember back to 8th grade, potential energy is stored energy. So electrons flow from the electrode with a more positive electrode potential to one with a more negative electrode potential, or a smaller electrode potential. Sort of like in a waterfall. The water moves over the top of the waterfall that has a higher potential energy to the bottom of the waterfall, bottom of the waterfall with a lower potential energy. So standard electrode potentials are all compared to hydrogen. So the standard hydrogen electrode has an electrode potential of 0 volts. And here's the reaction that shows the standard hydrogen electrode, or the potential for being reduced. So hydrogen ions gaining electrons, reduction goes to hydrogen. The standard electrode potential for this reaction is 0 volts. A volt is equal to 1 joule per coulomb. So one electron, remember, has a charge of 1.6 times 10 to the negative 19th coulombs. So when you have a standard half cell means you have 1 molar solution, 1 mole per decimeter cubed, or 1 mole per liter. You have 100 kilopascals of pressure. You have pure substances. You have a temperature of 298 Kelvin. And for half cells that do not include a metal, you use platinum for the standard half cells. For those standard half cells, you can find the reduction potential. So the cell potential, the E of the cell, or the voltage through a cell, is going to be equal to the potential at the reduction minus the potential at the oxidation. So it's the potential difference between two electrodes, and we also call this the electromotive force, which means that it causes the movement of electrons. Sometimes you might even hear it called the voltage. The more positive the value of E cell, the greater the tendency for reduction under standard conditions. So the standard reduction potential, E red, is the potential for reduction at that electrode. It's always written as reduction reaction, so you never switch from reduction to oxidation, and I'll see what I mean in a second. So to find the standard potential of a cell, you take the reduction potential at the cathode minus the reduction potential at the anode. So here's an example. Zinc solid plus copper ions goes to zinc ions plus copper. The E cell for this reaction is 1.10 volts. So when you hook these two half cells up in a voltaic cell, the voltmeter will read 1.10 volts across that wire. So where do we get the E-reds from? Well, the standard reduction potentials come from a table that looks similar to this, okay? And those reactions that are at the top have the higher reduction potentials, and those at the bottom have the lower reduction potentials. You can see that hydrogen is here at 0. Everything's based off of hydrogen. And what you do for these problems is you look up on your reduction potential table what is being reduced. One thing that's really important is that changing the coefficients in a reaction does not affect the value of the standard reduction potential. So you'll see what I mean in a minute. We do not multiply ever in the calculation of the cell potential. One other thing that you have to know for voltaic cells is standard notation. So sometimes you'll see chemicals written with these funny lines between them. And what this does is it just simplifies a voltaic cell. So what this does is you put the material in the anode first, separate it by a line. You put the products that are being made at the anode. You separate it by 2 lines. That means a new half cell. You put the products being made at the cathode, separated by a line, and the cathode to the right. Okay, so here's an example. Hydrogen gas, so at the anode, separated by a line. Hydrogen ions, separated by 2 lines. Copper ions, separated by a line, and copper at the end. So one half cell is hydrogen, one half cell is copper. So here's an example of calculation of a cell potential. For the zinc-copper voltaic cell, we have the following reaction. zinc plus copper ions goes to zinc ions plus copper. E cell is 1.10 volts. Given that the standard reduction potential of zinc ions to zinc is negative 0.76 volts, calculate the standard cell, the reduction potential for the reduction of copper ions to copper. And then we're given the formula for that reaction. So again, our formula is the standard reduction potential of the cell equals E red minus E ox. So the first thing we need to do is decide what is being reduced and what is being oxidized, just like most other voltaic cells or redox problems. So zinc is going from zinc metal to zinc plus 2, which means that it's losing electrons. So the zinc is being oxidized. The copper is going from copper plus 2. It's gaining 2 electrons to become copper metal. So this must be reduced. So if E cell is equal to E red, or E at the reduction, minus E of the oxidation, we know they give us the E cell, 1.10 volts. We don't know the E of the reduction, the potential of this reduction of copper, but we do know the E of the oxidation because zinc is being oxidized. And even though it's being oxidized, we still use the number for the reduction. So we plug that in. And then you can solve for the standard potential for reduction at copper by just subtracting from both sides. So 1.10 volts minus 0.76 gives you 0.34 volts. Here's another example of a standard cell potential calculation. So calculate the standard cell potential for a voltaic cell for this reaction. So dichromate plus 14 hydrogen ions plus 6 iodide ions goes to 2 chromium ions plus 3 iodine molecules plus 7 water. So again, we are still going to use the same formula as we did in the first one. And first we need to determine what's oxidized and what is reduced. So the chromium in this reaction is going from plus 6 to plus 3. So if you go through and assign your oxidation numbers, you'll see that. The iodine is going from minus 1 to 0. So it must be losing electrons. So the reduction reaction is occurring with the chromate, the dichromate. The oxidation reaction is occurring with the iodine. Okay, and you've seen this reaction multiple times when we balanced equations. So the chromium is being reduced, the iodine is being oxidized. So E cell is equal to the standard reduction potential for the reduction reaction minus the standard reduction potential for the oxidation. So we look on our chart, we find this exact reaction, E red is 1.33. We look on our chart and we see that iodine being reduced is 0.54. So take a second just now to try and flip back to the slide with reduction potentials, or the one that I gave you, and see if you can find those numbers. Now all we have to do is plug them into the formula for the standard reduction potential of a cell. So E cell is equal to the E of the reduction minus the E of the oxidation. So E cell is equal to 1.33 minus 0.54, which gives us 0.79 volts. So these two half cells, if you hook them up with a voltmeter, the voltage will read 0.79 volts across that wire.